Now we are going to go through the validation, and validation is, as most of the textbook says, that validation is the most important task in a simulation project. Okay, so developing a simulation model is an art, and if you have a correct conceptualized model in your mind, you can always translate it into a software in a few hours, maybe, not a very long amount of time. But validation is much more important, because if the model is not validated or if the model is not correct, then decisions made on this model are going to be very dangerous for the original system. So what is validation? The validation is the overall process of comparing the model and its behavior to the real system and its behavior. So we have either the conceptualized model in your mind, but operational model, it works as well. Because after verification, you are sure that the conceptualized model here and the software model are the same after the verification. Now the next step is validation. Now these models, the conceptualized model in your mind and the software model, computerized model, are they reflecting the behavior of the original system? So we are going to compare that model in the computer environment with the original system. So validation is comparing the original system with the model, not two models. Now we are using the calibration. It's an iterative process of comparing the real system to the model, and we are making adjustments. We are correcting the model as we realize the differences or discrepancies between the original system and the model. So we have a picture like this. We have a real system. We compare the model to the reality here, and we have an initial model. After initial model is compared and the discrepancies have been discovered, then we revise the conceptual model in our mind, again run through a verification process. The verification processes are usually short, my friend. Because of that reason, they do not seem as important as the validation process. Verifications are very easy with the current technology, with the plot diagrams and animations provided by Arena and the trace options. But validation is trying to make sure if you conceptualize your model in your mind correctly by looking at the system. So after making revisions, the new model is going to be a much accurate version compared to the initial model, and it is going to imitate the real system better, but still it will be needing revision, and with each iterative step of the calibration, the model is going to be reflecting the real system. As you see here, we have a real system shape here, and as we move forward at each iteration of the calibration procedure, the model that we create seems to imitate the original system behavior better, okay? But after some point, you need to stop, right? So it is impossible for you to develop a perfect model that perfectly represents the original system. So how do we compare the model to the reality? How do we compare the model with the original system? We can run subjective tests. So one approach is running subjective tests, and in subjective tests, we involve people who have knowledge about one or more aspects of the system and can make judgments about the model and its output. So basically it is telling us, ask the experts, show them your model, show the behavior of your model, and because they also have an idea about the original system, they are going to give you some updates, maybe some recommendations of correction. So these are subjective tests. So it changes based on the people who is involved in this test. Now there are also objective tests, which are basically statistical procedures. It says use the data on system's behavior and the data produced by the model. For example, you have collected the Q waiting times for entities in your model, but you can also collect these Q waiting times from the original system. Remember now, Q waiting times are not input variables. They are output variables, right? They are performance metrics. So we need to understand the distinction in a queuing system. What are the input variables? What are the output variables? So Q waiting times are output variables. We have collected output variables from the original system, and we also have the output variables, Q waiting time, generated by our simulation model. Now we need to check if these two data, they conform to each other. So are they having the same distribution? Are they having the same mean and same variance? So this is a statistical procedure. So basically we are comparing the output variables. So we are collecting output data from the original system and output data from the simulation model, and we are comparing the conformity of the output distributions. So we collect data on the system's behavior and the data produced by the model and compare some aspect of the system with the same aspect of the model by statistical testing. I mean, by the way, you can compare many different things. There are maybe several, maybe hundreds of different output data in the system, right? So it is not saying that compare all of them. So you need to compare a few of them, a few important of them. And once you are sure that some of them are conforming the output properties of the original system, then you can say that the rest is also, the rest should also conform to the original system. So for objective tests, we should not use the system data that is used in input modeling. So this is important, my friends. Let's just say you have collected 20 days of data from the original system. And using these 20 days of data, you have developed some input model for your simulation. And in that simulation model, you have run some tests, you have verified it, and you want to be sure that it is validated. And you are going to use the output data that is generated from the simulation model and compare it with the output data of the original system. But please do not use the same 20 days of data to collect the outputs now. Another 20 days maybe. So it is basically saying this. If you want to have objective test, there should be a input modeling data and the validation data should be different. So you need to collect 40 days of data. For the first 20 days, let's just say, you are going to use this for 20 days to develop your input models. But after developing your model and collecting some output data from your model, you are going to compare this output data with the second 20 days of observations. So otherwise, you may end up with wrong results because of the correlation. So there is a correlation between the input data and output data in the first 20 days, right? There is a correlation, and that correlation, unfortunately, can create erroneous results, and you may end up with the wrong model in the end. So it says collect a new set of system data to be used at the final stage of validation. So we use data set 1, the first 20 days of data, to input model development and calibration procedures. And once we are sure that the model is verified, then in the final validation, we compare the output data of the model with the output data collected from the second data set. Okay, it should be a different data set. Now, validation induces cost. So with every iteration of validation, with every correction in your model, there will be a cost. So it is going to take some time to update, to make it perfect. But as you get closer and closer and closer to the original, the marginal contribution of a new iteration in the validation is going to be less and less. Once you are sure that you are close enough, your model is valid enough, then you need to stop. Because each revision involves some cost, time, and effort. So the modeler needs to weigh the trade-off between the model accuracy and the cost of a validation overkill. So it do not overkill the validation. I mean, when you intend to create a perfect system, imagine you are drawing a perfect paint of a natural scene. And as you want to put more details into it, then the painting is going to be less beautiful. So the more details you want to put inside it, at some point you need to stop. Okay, every painter stops at some point. They do not put birds everywhere. They do not try to draw little insects over the trees. So just like that, a validation overkill is going to create costs, and then you will realize that creation of the simulation model is going to be much more costly than you are going to save from the solution of your problem. So if a satisfactory accuracy cannot be obtained with a reasonable cost, so let's just say you have spent so much money into the validation process and still you realize that the model that you developed is not satisfactory, it is not valid. So what you can do, either you reduce your accuracy expectations or you abandon the model. I mean, then maybe the simulation is not the correct technique to solve that problem. So at some point you need to realize that. But with the current coding technology, I mean, we are talking about the simulation discipline, which is developed from 100 years ago here. Now, currently you have advanced software such as Arena, which are very flexible to create many models. I mean, you can create many different valid models for even for complex systems.